Oh, it's sports ball time. If you're like me, you're now thinking about the superb owl this weekend. Oh, what a good bird. And a question that crossed my mind, a ridiculous one, as we want to do on this program. What would it take to kick a dang pigskin to the moon? Or to space, rather. How could you kick a football off of the surface of Earth and score a field goal in the cosmos? Yeah. Well, if we want to consider this question, we want to be very good physics students and first ignore the atmosphere because it's complicated. And if you ignore drag and air resistance and that kind of thing, the problem is a lot easier. It's almost impossible to kick something out of the atmosphere if there's atmosphere. So we are considering no atmosphere and a regulation size American football, and we are going to kick it from the surface. Let's say it's at Lambeau Field. I don't know. I'm from Wisconsin. So let's say it's at the historic Lambeau Field. They should be in the Super Bowl. And we want to kick a football out into space. Well, how hard do we need to kick this football? How much energy should be going into it? Well, you can see from my equation down here, this is how we determine the escape velocity of an object. So let's go through that because you've probably seen escape velocity. You might even know the value, but do you know where the value comes from? So we can do a basic conservation of energy analysis here to figure out how much energy we need to put into a football if we want to kick it into space. So at the beginning, when it is at the surface of the Earth in Lambeau Field, go Pack Go, the ball will have some kinetic energy, K here if it's moving, and it will have some gravitational potential energy near the surface of the Earth initially, I. And then in the final state, when it is escaped the Earth's gravity, we would want it to have some kinetic energy, and it would then have some potential energy. However, because gravity acts on everything everywhere, no matter how far away it is, to calculate escape velocity, we need to do something with these final terms. In fact, we have to assume, basically, well, not basically, we have to assume that at the end of its journey, the football has sped down all the way to zero, and it is so far away, and gravitational potential energy is negative in these equations. It is so far away, it is infinitely far away, such that it has no gravitational potential energy. And so what we get, because the gravitational potential energy is negative, we reference the Earth, the closer you are, the more you have. So we are going to get kinetic energy is equal to gravitational potential energy here. Now, if you watch this program, we've gone through kinetic energy many, many times. It's 1/2 mass of the object, velocity of the object squared. And this, in its full form, is going to be gm mass of the Earth times the mass of the object divided by the radius, the distance, Earth and stuff. So we can solve all of this and we can get the escape velocity. It is equal to the square root of 2 gm over r, because the mass cancels out, the mass of the object. So that's an interesting note, two interesting notes. The mass of the object doesn't matter. It still has the same escape velocity if it's on the same body. And this is independent of direction. Even though this is a velocity, we call it escape velocity, it's actually an escape speed because it doesn't matter. The escape speed, the escape velocity doing this is exactly the same as the escape velocity doing that. And if you know, velocity is a speed with a direction vector, so these are different velocities, but they're the same value, which makes them speeds anyway. So if we do this for values for Earth, we can get escape velocity for Earth, which is 11.2 kilometers per second, which is incredibly quick. It's so fast. It's so fast, in fact, that if you fired a bullet at one of the end zones during the Superb Owl, I can't say it because of legal reasons. At the Superb Owl, if you shoot a gun at the end zone, the bullet wouldn't even have traveled like 10 yards before something moving at escape velocity would have scored a touchdown. It's so fast. So this is the escape velocity. Now, if we want to know how much energy it's going to take to kick a football and to give it escape velocity, one basic way of estimating that is what would the kinetic energy be of the football when it is at escape velocity? How much energy would we need to transfer into it? And if you do that, you get a value. Let's do a different color. You get a value if you put the mass of a regulation football going about 0.4 kilograms into a kinetic energy equation with 11.2 kilometers per second. You get 25 megajoules of energy, 25 million joules. Now, without any context, that doesn't mean a whole lot, right? Oh, mega, that sounds big. Well, it is big because this is twice as much as a 2-ton car moving at highway speeds has in kinetic energy. So imagine how hard Adam Vinatieri, is he a sportsman?
Yeah.
He was a kicker, right?
He's a kicker for the Colts.
Oh, imagine how hard Adam Vinatieri would have to kick a football so that his foot is basically like twice a highway speed car collision. Ah! A human couldn't do it. A human would not be able to kick a football to space, especially when you consider the atmosphere. This is Superb Owl Math. Hello and welcome to Because Science Live, the live edition of this program where I take all your comments, questions, and corrections off the top of my head and try to be interesting and entertaining and see if we can say something that we regret later and you'll tweet at me. Look, I'm just Kyle, all right? I don't have a PhD. I'm not a working scientist, but I do know I do know a little bit about a lot of sciencey and pop culture-y things. So if you have a question for me and you're watching on YouTube, please put it in the YouTube chat. Do not spam the chat and ask good questions or else I'll never, ever answer you. We have Voice of the Void Nate here to get to your questions.
What's up, Kyle?
Oh, just thinking about the big game.
The big old game.
Man, the 49ers destroyed my Packers, and it felt bad.
Well, the Packers hurt my Seahawks, so I mean...
Yeah, I'm fine with it.
Okay. Some people are debating if R is squared in that equation.
Oh, is it?
Some people are saying yes, some people are saying no.
It's not. So, what you are referencing here is this looks very close to the, universal force of gravitation, and then you would be right. GMM over R squared. That is showing that the force of a gravitational force on an object depends with distance. But when you want to, this is going to be messy, but when you want to translate a force into an energy, you can consider it like a work energy equation. And when you do that, you have to multiply. Remember, we've already done this, so this is don't say that I'm wrong. But if this was a force, we have to multiply the force over a distance, and that distance is also R. And so we get the cancellation of the R's and we only have one R. So this is the gravitational potential energy, one step removed from the the force of gravitation. So I think that's where the confusion is. Or I have that completely backwards, but I think I have it right. I'm pretty sure.
From Axel3815.
Oh, cool name.
Hey Kyle, love the show.
Hey, thank you. Obligatory comment.
If a star goes supernova.
Oh, recent episode of. Yep.
this channel, yeah.
This very here.
Could a planet in its system stay whole, or would it break apart?
So what we didn't really get to is that if we have our football sun here, if we have our football sun here, and it was emitting neutrinos from. Oh, sorry, I have a little bit of. Okay, so if this was emitting neutrinos, we were going through mostly what the neutrinos would do to everything on the planet. They would deposit enough energy in all the organisms and all the material to vaporize it. But remember that once this football sun explodes, all the light and all the material from the star itself, the star, the gas and the plasma, like think about a coronal mass ejection, but the entire mass is ejected. All of that is closely following the neutrinos. I mean, a few hours later, it's going to reach the Earth, and that shock wave and that light is probably going to destroy the planet. So, no, not a whole lot of hope. I get what you're saying. Maybe you could go like underground or something. The neutrinos would still get you underground. They would hit this side of the Earth, and because they're so weakly interacting, they would pass through the Earth and hit everything on the other side too. So there's really no stopping it. I remember someone that I forgot to include in footnotes, but they were like, hey Kyle, that's kind of scary because, like a star could go supernova or a gamma ray burst could happen, light years away, and it could be already traveling directly at Earth, and we wouldn't even know it, and then we'd just all be dead in an instant. Yes, that could happen. But space is so big, the chances of that happening are vanishingly small. Think of how precisely directed a gamma ray burst would have to be if you're trying to hit a single planet light years away. It's an unfathomable. Next question, man.
From Justin Eck.
Why can't I say fathomable?
From Justin Eck. Could we use rocket boosters at the North and South Poles to speed up Earth's orbit so we don't need leap years? It's a valid question.
Sure. I like your tenacity. Let's say that. But if you probably know that if there's like a big enough earthquake, you can upset the motion of the planet. You can add or subtract like seconds to a day if the earthquake is big enough. And what you are talking about is replicating that kind of energy, and it would take more than a large earthquake to cancel out leap years and leap seconds and all that jazz. So you're talking about concentrating an earthquake's worth of energy into something that we made, probably using chemical energy or something like that, if we were using today's rockets. Now, think of the size of this rocket. Think of how much fuel it would need. Think of how many rockets you would need. Think of could you even connect something with so much force to the ground without it shooting off into space at escape velocity? I don't think so. The engineering here would have to be absolutely monumental. Although, you could try I have this wrong, because you said, okay, so if it was North and South Pole, because the Earth spins on an axis, roughly North and South Pole, not like magnetic North and South, but the axis of rotation isn't always exactly, it's almost never exactly North and South. But if you're rotating the Earth, if you put it on a North Pole and you launch a rocket, the Earth's going to go this way, but we rotate this way around the axis of that pole. So to answer your question exactly, if we put a rocket on the North Pole, you would tumble Earth in a different direction and probably cause terrible natural disasters? I don't know if it was even possible. What you want to do is put rockets on the equator facing one direction or another to speed up or slow down the rotation of the Earth, because this is how we are basing our day off of, how long it takes the Earth to rotate once going around the sun. So no and no. I don't think so. It'd be ridiculous.
Some people are asking about Dr. Moo.
No!
I just want to give an update that she is actually in Florida.
Yes. So Dr. Moo is, unlike me, she's like a really smart scientist person. So Dr. Moo has a full-time job, and right now she is in Florida, and I don't know how specific I can get, but she is in the same area as the Mars 2020 rover, helping officially. I think that's all I can say. But Dr. Moo has a full-time job doing incredibly important work, like landing robots on Mars and crap. So Dr. Moo is busy, but I believe she will return soon with some more episodes of Because Space. We haven't forgotten about her. I never forget about Dr. Moo, all right? She's lovely. But she is also busy, advancing humanity and stuff. And what am I doing? Kicking footballs in space. Land that on Mars. Moo. That is your real
Got
name.
her.
Got her. It is
Sick
a real
bird.
Yeah.
I cannot pronounce this name, so just K.
Oh, feels bad, man. That was one chance.
How's Kyle's resolution about reading going?
Good.
Any new books to share?
Good. Yes, so I resolved to read one book a month for this year because I don't read enough and I feel dumb. I get trapped scrolling on my phone and not thinking about my feelings and being introspective, so I wanted to read more. And the book that I finished for January was called Neurotribes, a history of autism and the legacy of the neurodiversity movement. It's a history from the beginning of the first conception of autism and the autism spectrum all the way through to today. So going back to like World War II, World War I and before, with Dr. Hans Asperger, and going through all of the diagnosis and how it changed and morphed and evolved and how it was defined and what people go through and what pop culture did for it. It is a fascinating book, very long book, but it's basically a history of the condition. It's called Neurotribes by Steve Silberman. If you're interested, it won a number of awards. It's very good. So that one's good. And I also resolved to do 100 pull-ups a day. So far this month I've done 1,500 pull-ups, or like 2,000, something like that. I can't pull up on here. There's nothing. I kind of just float.
From the plane shifter.
Ooh.
What would Earth look like with rings? Can a planet the size of Earth even support rings?
Huh. I don't know. I'm probably wrong, but I think there is a mass requirement for something to have, if you want to look this up, because I won't have the actual answer for you. But I think the Roche limit, or Roche, I've never said it out loud. The Roche limit describes how close you have to be to a gravitational body to have the gravitational forces tear an object apart and form rings. So, for example, if a giant asteroid was in a certain orbit around like Saturn, and it came within the Roche limit, the tidal forces of Saturn would act to break it apart and it would become part of the ring material. Now, I do not know for sure, probably, if I had to guess, it must, but I think the Roche limit is mass dependent, and I don't know if Earth has enough mass to make that happen. It probably has a Roche limit, but it might be super, 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 super close such that it doesn't matter. So you'd have to look it up for what it is for something like Earth, and therefore I do not know. But I know this is the term that you want to look up. I just do not want to say bad terms or not. And I think a number of artists, I think especially on Reddit, you can find some viral posts of, they've done renditions of what the Earth or what the sky would look like if the Earth did have rings, and those are fascinating and very beautiful. You should look that up. Roche limit. Last question?
Last question.
Woo!
From Opium Daydream.
All right, hey man.
Pretty dope.
Live your life. It is pretty dope. Good one.
What happens to the air inside of the football when it goes into space?
It might explode, actually. You know, I mean, you've probably seen this occasionally, maybe. Have you ever seen like a balloon released into space or released just straight up? It will pop at a certain point, and that is because as you go up and up and up and up and up and up, the pressure inside, well, you know, basically atmospheric pressure. The pressure, 14.7 pounds per square inch, more or less, inside of the balloon starts to become more than the pressure outside of the balloon. And if it got into the upper atmosphere, like 100 kilometers up, then it would be encountering like no pressure. And at that point, it is upon the material itself to withstand that pressure. So something like the International Space Station is pressurized at atmospheric pressure, but it's built strong enough and with good materials such that that pressure doesn't rupture the thing. Balloons are not made like that. So 15 pounds per square inch on a balloon with zero things pushing around it to keep it in a balloon shape, it would pop. And so you've probably seen balloons be released, and at a certain height in the air they pop. And so I forget what the original question was. Oh, yeah, so the question is, could a football hold 14.7 pounds per square inch or so in space? I forget what they are pressurized to. I think it's beyond atmospheric pressure, so they're pretty robust. Even like a soda can, or even like a 2-liter soda bottle can be at like 90 psi before it ruptures. So I think if you kicked a football into space, I don't think it would explode. It would just stay. It would kind of blimp up a little bit, but I don't. It might not rupture. That pigskin is pretty thick. It's not. Well, thank you for joining me for another edition of Because Science Live. Whew, we did a lot. This has been what a January this has been. Jeez. I hope I've been some sort of entertainment and levity in this year 2020. It's a doozy, and I usually say, you know, what's coming up down the road, but you know, because 2020 has been rough, and I don't say this enough. We've done over 100 live streams of this, which is the hardest thing that I do. It's hard to talk consistently and coherently for 20 or 30 minutes. Over 100 episodes of this, over 107 episodes of Footnotes, 281 episodes of Because Science. I've been doing it for 5 years. If no matter for how long you've been watching, supporting, if it's your first time, if you've ever showed it to friends or your children or in a classroom, anything, thank you so much for being a part of this geeky journey, and I cannot thank you enough. It's my whole life, and I'm not a spiritual person, but I think this kind of stuff, even though it's silly, it's what I'm meant to do, and I try to do it. So if you're watching now, just want to say thanks, and I have to do that because this is all we got.